Okay, so this is the idea of a hash function. Now let's see how we use this hashing idea to have an efficient data structure to help us to answer those dictionary type of operation queries. Okay, again, what are the dictionary operations? So we have some universe of elements U, and but I want to only store a subset of them. Okay, and I want to be able to perform the query operations such as search. This is a membership. Queries, and I want to be able to insert and delete those elements. Okay, so all right. Okay, let's see that first, suppose this is what we want to do, and in general, based on what we already learned, what can we come up with? What can we, how can we handle these operations? Okay, so here's the first very simple approach called approach 0. Okay, what I can do is that I can use an array to organize all the keys that you want to store. Okay, let's assume for the time being that the keys, the elements of interest, let's assume all the elements that you're interested in are numbers. Okay, if they're numbers, then we said earlier what we can do is that I use the array of all these numbers, and I could pre-process them by pre-sort the array in, if I have n elements, I can pre-sort them in n log n time. So now I have a sorted an array. And once I have it sorted for search, if I need to search for a specific key, I can just perform binary search in the sorted array, and that is log n time. Okay, how do we do insert and delete? Well, here's a bit tricky. Insert, we can just add it into the array, but then note that we need to make sure the array is still sorted. Okay, so then after you insert a new, you cannot just put a new element in the end of the array. Okay, you have to then insert in the correct position. And worst time, this can take a linear time. Same for deletion. When you remove an entry, then you left a gap over there. Then you have to shift your array to close that gap. So both of this, unfortunately, as we said earlier, sorted an array is not good for dynamic operations. So insert and delete will take linear time, but for search, it's very efficient. Okay, so this is our first approach. Okay, not great. All right, let's say that the second approach is that I can use the standard doubly linked list data structure. Remember that this is a list where every element has 2 pointers, one pointed to the element after it, the other one to, so every element has one pointer point to the elements after it, but it has another pointer point to the element before it. Okay, so this is doubly linked list. Okay, and let's say this is the head of or your list, and the last element linked to nil, the empty, and this is the tail. Okay, so this is standard data structure. And the pre-processing is easy. Once you are stored there, there's nothing that you need to do. And for insertion, I simply, if I have a new element, say key that you want to insert, what I can do is that you can insert either at the head or the tail. What you could do is that you simply say, okay, I'm going to create a new one with this key, and then my previous tail, I now point at the key, and then this one, the one before it, I go to the previous one, and then this one now becomes a tail. Okay, so this only takes just constant time, updating some pointers. Okay, so in other words, insert takes only constant time. Okay, delete. If I know which one delete, suppose I know that I'm going to delete this entry. What do I need to do? So I need to delete this one, let this one to be the element before it, and this is after. After I delete it, I simply update this one, the pointer, the next pointer to point to Z, while for Z, the previous pointer, I point to Y instead of to X here. Okay, so again, I only need to update constant pointers. So delete also take constant time. Okay. The problem is, so both of insertion delete, this dynamic operation for array that was very slow, but now for linked list, it's very easy, okay? The problem is for search, because now there's all this element just in arbitrary order. If I want to search for specific key, whether it's inside stored in this linked list or not, I have to then linearly scan from the head and follow the pointer and check one by one till I find it or till I reach the tail, in which case it's not in it. Okay, so search is unfortunately very slow, which takes linear time. Okay, so compared to the array, now dynamic operation is efficient, but search is slow. Okay, of course you may say that, well, but we already learned something better. Indeed, we said that if I'm going to use a balanced binary search tree to store all these numbers, okay, then we didn't talk about the set up a binary search tree. Okay, a balanced one. And that takes n log n time, same as sorting. Okay, we didn't talk about it. But still, once it's set up, then to do search and insert and delete, it's all very efficient. All of this are log n time. So better than the array and the linked list that we've seen so far. Okay, all right. But here is yet another idea, okay, which intuitively can even do better than the binary search tree, which is log n time complexity, okay? In particular, this is something like called direct address tables, okay? So let's for the time being assume that the universe is not so huge. Let's say you want to store the keys that you want to store as zip codes, okay? We know that the zip codes are 5 digits, integers, right? So we know that, okay, all possible zip codes has to come from 0 to n equal to about 100,000. Okay, so this is the size of my universe. Okay, so in this case, if I know that my size of the universe is basically small, it's only about 100,000, okay, what I can do is that I can simply use a big table. This is called a direct address table of size. This is 0. This is size n of 100,000 size. Okay, now, and what am I going to do? For every zip code you give me, okay, let's say that you want to store, so this is array A, okay, let's say that you want to store, so I will go to store, let's say, zip code 22330 12345 90000. Let's say you want to store these 3 zip codes. What do? You simply go to the entry, you use the number you want to store as the index. You go there, you said that, okay, if this one is in my input, then I put 1 here. Okay, same. So this is the index 1, 2, 3, 4, 5. You put 1 there. And this is 9000. You put 1 there. Everything else is all 0. Okay? So in other words, the number that you want to store now is used as index. If that number is in your list that you want to store, you simply go to the corresponding entry in your array and then put a 1 there. Okay, otherwise it's 0. Okay, it's a very simple approach. And let's see, now if I want to do search, okay, let's say I want to search for 22330, what do? I simply go to this entry. Okay, if it's 1, that means yes, I have it in my list. If it's 0, that means I don't have it. Okay, or let's say that suppose I want to search 10000. So I simply go to the entry. Let's say this one is the index 10000, and I go there and I see, oh, the entry is 0. So I simply return. Okay, if it's 0, that means it's not in. If it's a 1, it's in. Okay, that's it. Okay, now how do I do insertion and deletion? So search, as we just said, since we just go to that, whatever you are searching for, you just use that as index and go to that entry in the array. So this only takes time constant. You need to get it. Okay. How do you do insertion? Let's say that if you want to do insert, say 10000, okay? What do? You simply go to the entry, you simply set, you go to that corresponding entry. And if it's it put that one entry to be 1, means that now you have this element. That's insert, okay? So this again only require one direct address access in the table. So that takes also constant time. Okay, deletion. Now suppose I want to delete this element. Okay, what do? I go to the corresponding entry and I set it to be 0, means that it's gone. Okay, so deletion also is just one array access. Okay, also take constant. So this is great. What did we say? Essentially, the trick we're using here is that we're now converting suppose the elements you want to store are all numbers, and suppose you know the size of universe is fixed. Okay, then I can simply use this as indices into the array. Okay, I just open an array of the size, which is size of the universe. So I prepare for everything in my universe. Okay, then when you search or when you insert or when you delete, you just go to the corresponding array entry and adjust it accordingly. Okay, all of this operation take only constant time, which is great, which is better than all the previous approaches we talk about. Okay, what is the problem of this approach though? Okay, so now you can pause and think about what is wrong with it. Why don't we use this approach all the time? Okay. Well, you may have already noticed that the problem is that here I have assumed that in this case, I assume that the universe that I'm having, which is only of a size 100,000. In general, if your universe is large, okay, then you have to have a much bigger array in order to support this. Basically, your array A has to be the size of the universe. So if my universe is all possible words in English, then that's a huge space. Okay, then you cannot really afford to have that size. Okay, number one, you may not be able to afford to open such a huge space. Okay, number two, it may be very inefficient, because you may only care about a very small, the numbers that you ever care, or maybe the English words that you ever care is only a very small subset. What's the point of having such a huge array to prepare one entry for every possible word? Okay, so it's not very practical for when our universe is large. Okay, but this approach does have advantages. Okay, which is that if we can do this, then all these operations become very efficient. Okay, so the question now is that, can we kind of still use this idea, but then address this issue that right now I need to have an array of the size, which is the size of the whole universe? Okay, so can we still leverage this direct address idea? Okay, and it turned out that yes, indeed we can, by using hashing, use hash function to help us. Okay, and the resulting data structure is called hash table. Okay, so in particular, what do we have here? Again, let's say that the U is your universe of all the elements that you want to see. Let's say that the U is all the possible stars in the sky. Okay, you want to be able to store potentially a subset of them. Okay, now a hash table is actually a table of a fixed size. Let's say of a size M. Okay, and the goal is that the size M is much smaller than the size of your universe. Okay, so now in general, in practice, we are going to choose M to be about the size of the data we will see. Namely, your universe, the universe is all possible stars. But let's say that you are only going to study the stars that ever appeared above your house. Okay, that's a very small subset of stars. So in general, the value m, your hash table size is usually chosen to be about the size of the data the size of data you're going to see. Okay, all right. But how do I map from the universe to only this small hash table? I'm going to use a hash function. Okay, this hash function will map from the universe to one of the indices in this hash table. Okay, so for example, the hash function could map all the words in English, each word in the English, to a number from, say, 0 to 100. Okay, so that's what this hash function is doing. Okay, once we have this hash function, then if you have an element u, if you now have an element, say a key in your universe that you want to store, okay? Now I'm going to use this direct address table idea. Now I'm going to instead, I first hash it. Now this become a number from 0 to n-1, right? Now that become an index in my hash table. I simply store it in my, so if I want to insert, I simply set this one. I stored in my hash table. Okay, so basically, if my universe is like zip code, only from 0 to 100,000, then I can use that zip code directly as an index into a array A to store it. Okay, but in general, we don't have this luxury. Our universe can be very huge. Okay, and we don't want to have a table of size of the universe. Instead, we say let's perform one hash to map the universe to a fixed size table. Okay, to the indices to this table, and now we can, given the element, we can just use its hash value as the key and store it in the as the address in the table and store it in the corresponding table entry. That's it. Okay, so this h of key is called the hash value of this key k in your universe. Okay, that's it. Okay, all right, we're going to look at examples to make this more clear. Okay, there's one thing though before I move further, is that because the hash table is can be much smaller than the universe. Okay, then it's possible that multiple keys in your universe can hash to the same slot in the hash table. Okay, and when that happens, we say that a collision happens, namely two different elements in your universe now got mapped to the same slot in your hash table. So they both want to take that slot. Okay, so when this happens, it's called a collision happens. Now, in our data structure, in order to store all the numbers, okay, we're going to store in this hash table, but then different elements may be hashed to the same entry. So we have to have a strategy to handle this collision, okay? And there are different ways to handle that. A simplest one is called the chaining, a chaining strategy using the chaining strategy to handle collisions, okay? So we are going to use this chaining strategy in our description of the hash table. Okay. In particular, what is this chaining strategy to resolve collision? Well, if you have multiple keys hashed to the same entry, okay, so in this case, what we have is that the hash value of K1 and the hash value of K4 both got mapped to the same value here. Okay, so then if there are multiple keys got mapped to the same index, we simply store them there by using a linked list. Okay, we just chain them together. So we just use them. Okay, we just use a list to chain them together. This is called resolved by chaining. That's it. Okay, so here is an example of your whole universe is pretty large, but the actual keys that you are interested in, K1 to K8, only a subset of them, okay? In order to store them, you perform the hash. You perform the hashing to hash each of the key to indices in this hash table, and then you store that key in the slot corresponding to its hash value. Okay, if there are multiple keys got mapped to the same slot, they have the same hash value, you simply list them all there, chain them together using a linked list. Okay, that's it. Okay, so this is our hash table data structure where collision is resolved by the chaining strategy. Okay, all right. And if a hash table entry doesn't have any key mapped to it, then you just put a neo pointer. Okay, so it's just a neo pointer. Okay. Okay, so let's look at a concrete example. Okay, let's for the time being say that my universe is simple, it's infinite, but it's simple, it's just the positive integers. Okay, and my hash table is very small, it's only a table of size from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My hash table is only of size 11, okay, from 0 to 10, okay? And what is the hash function I'm going to use? I'm going to map the whole universe or possible integers to one entry here. And I have many different choices. Let me choose a very simple one where h of k is mapped to, you simply take this value modulo 11. Okay, you basically divide by 11, take the remainder. Okay, so let me write it well. So the hash function I'm using is k mod 11. Okay, so that's a hash value we're going to use. Okay, let's say that suppose now you're given a list of the numbers that you want to store. Okay, let's say that it's a 5, 21, and let's say 32 and 7 and 18. Let's say this is a list of numbers that you want to store. Okay, what do I do here? Well, for 5, where do I put it? Well, you need to compute what is h of 5. And 5 modulo 11 is still 5. That means that 5 should go to position 5. So you hand it here. You say, I have 5 stored here. Okay? Next element is 21. Where should I put in the hash table for 21? Again, you map it to use the hash function, which is 21 modulo 11, and that's 10. That means that 21 will be stored in the index 10 position slot. So you say that I'm putting 21 here. Okay, all right. Next, you have 32. You say, what is the hash value of 32? Well, hash of 32 equal to 32 modulo 11. And that's basically, again, we get a 10. In other words, 32 should also go to slot with index 10. Okay, so you go there, let's say we just use a single linked list. Now when I insert the 32 in this list, let's say I move 21 down, depends on how you implement the list. If you're in Python, the list is implemented using dynamic array, in which case that when you insert 32, you'll just put it in the end. Okay, but if you use a singly linked list, then that's usually inserted at the head. Okay, so you simply hand 32 also in this list. Okay, and then we have 7. The next element 7, h of 7 is 7 modulo 11, which is just 7. So element 7 is stored here. Finally, we have 18, and we find what's its index? H of 18 is 18 mod 11, which is also 7. That means that 18 should also be stored here. So that's it. So this hash table T of size only 11, but we can use this to store a set of all possible integers. Okay, where the integer can be any integer, doesn't have to come from 0 and 11. Okay, again, as we see, the hash function is to map my huge universe, in this case, it's infinite size, okay, possible integers, to a simple integer from 0 to 10. And those are going to be used as indices into my hash table. That's it. Okay, and this is in the end how we store it. Okay, questions? Okay, now before I move on, now you should think yourself, how do we do we now have a hash table to store all these numbers, okay? But how do I perform the dictionary operations that we're interested in? Okay, let's say that, how do you perform search? Okay, let's say, suppose now I'm asking, is 18 in the list? Oops. Okay, unfortunately, let's see how do you, okay. Okay, so how do I search for element 18? Okay, what do? Well, you said that if 18 is in this hash table, where should it be? We know that if the 18 is in the hash table, it should be stored in the spot h of 18, right? That's where it should be. And h of 18 is basically 7, okay? So what do you need to do? You need to go to the slot in your hash table corresponding to the hash value 7, okay? That gives you a list of all the keys got mapped there, okay? How do I search? I need to search now in this list. Is 18 inside or not? Okay. In this case, I check this list, 7, not 18, but 18, yes. So that means that, okay, we return yes. Okay, so we basically return is 18 in this entry, this list of your hash table. Okay, in this case, 18 is in, so return yes. Okay, if instead you are searching for, say, 16, okay, what do I do? First, I have to compute the hash value for 16, and that is 5. That means that if 16 is in my hash table, it should be stored in this slot. Okay, then we go to this slot and we search. We saw that there's 5 there, and then there's no more. That means that in this case, 16 is not. Then in this case, you return none. Okay, so this is how we do search. Okay, questions? Okay. All right. So in other words, the search is basically, you are searching for a specific key. You first find the hash value, okay, what's the index in the table, and then you go to that table entry. You check the list of all the numbers or all the keys already mapped there, then you search whether your element is there or not. Okay, that's what you do. Okay. And for insertion, it's the same. So if you want to insert an element X, okay, let's say that we're hashing in fact, let me just change this one to be, suppose where you want to insert a key K, okay? So I'll update the slides later. Okay, you simply compute its hash value, okay? And go to the corresponding table in the hash table, and then you insert this key at the head of it, or if you're using Python, it's going to add it probably in the end of it. Okay, just append it to the end of the array. Okay, doesn't matter. Okay, so that's it. Okay, you just insert it into the list associated to this hash table entry. Okay, and for delete, if you want to delete the specific one, okay, then you simply go to the end, the hash table, find this entry, and then from the that list, you find the entry and remove it from the list. Okay, so what is the time that we need for each of this operation? Well, for example, in search. For insertion, for example, I simply need to compute the hash value. Assume that only takes constant time. Okay, it's just a map. Okay, then you insert it at the head of the list, which also takes constant time. So insertion is very efficient, can be done in constant time. Okay, but for search, we have to first compute the hash value constant time, but then this can have a long, now we need to search the element in the list of all the elements mapped to this hash table entry, okay? And we have to, suppose we do linear scan, then the time we're going to spend to search for this element, essentially in the worst case, is proportional to the length of all the elements hashed to that entry, right? So if you have a hash table, and suppose for specific one, say this is you look at the hash value and it corresponds to this entry. Let's say this one has many elements already hashed here. Okay, then for me to find it, I have to go through them one by one if they're just stored using a list, and that takes time proportional to the length of this list. Okay, so that's the time we need. Okay, now in the worst case, what is this length? Well, in the worst case, suppose your hash table T stores n numbers. Let's say we're really unlucky. All the numbers that you're storing all got mapped to the same list, the same entry, okay? Then in the worst case, it can be linear time. Because, I mean, if all of them are hanging here and you're searching for specific elements there, you have to scan through all of them. The length of the elements mapped to the list of elements mapped to this entry is linear in worst case. Okay, so that's the worst case. All right, and for deletion depends. If you have to first find it before you can delete it, because deleting an element from a list, from say a linked list, is not a big deal. It's constant. But to find it in the linked list, you need to spend linear time to search for. So it's also length of all the elements linked to the position, the slot that you are looking for this element. Okay, so that's it. So both of these two operations, okay, worst case can take linear time, because worst case, you're unlucky, a lot of linear number of elements got mapped, hashed to the same position in your hash table, and you have to scan through all of them. Okay, all right. So this is the hash table and how we perform this different dictionary operations: search, membership query, namely, and insert and delete. Okay, all right. As we see from the previous slide, okay, the performance of this hash table operations really depends on the number of elements that hashed to each slot in the hash table. Okay, if you have one slot which has a lot of elements hashed to it, then when you search or insert to that slot, it can take a lot of time. Okay, it's proportional to the number of elements hashed to a slot. Okay, now in general, if I want to have a good hash table, okay, then I want to have a good hash function where hopefully it should spread elements into the hash table uniformly. Okay, so that no slot is taking too much, many more than others. Okay, what is the best case scenario? Well, if you have n elements that you want to store, and let's say your hash table has size only m, you have there only m slots, then what is the if I want to spread them evenly, that means every slot gets equal number of elements hashed to it. Okay, that means that ideally there should be n over m elements in each of the hash table slot. Okay, so if your hash table is of size m, and let's say if you have two m numbers that you want to hash, okay, then on average each slot should get only 2 elements. Okay, that's ideal. You want a hash function to spread them out evenly like this. Okay, you don't want that. You do not want that all of them are all like n. Most of them are all hanging here. You do not want this. Okay, you want to have a hash function to spread hash elements evenly into the hash table. Okay, so that's what a good hash function should do. Okay, on the other hand, we do not know what input data are going to given to us. So how do you design a hash function that can achieve this property? Okay, so this is not this itself is a separate topic that a lot of research is done, how to design universally good hash function. Okay, we're not going to talk about it in this class, but you can assume that we have reasonably good hash function works very well in practice to help to achieve that. Okay, so we'll take that as a given now. Okay, if you have we know that in the worst case, okay, if no matter what hash function you use, okay, I can always be really unlucky that all the elements got hashed into the same spot. Okay, so the worst case, the time complexity of insert and the search, of search and delete operation can take time order of n. Okay, but if we have a good hash function, we hope to have a good expected time expected time complexity. Okay, which we're going to analyze right now. Okay, so as I said earlier, if you have n elements you want to store, and if your table size is m, then this n over m is basically average numbers per slot hashed to each slot. Okay, each slot in your hash table will receive n over m number of elements. Okay, and as we said earlier, this is the best you can hope for. If you want to spread them out evenly, so nobody get a bad situation, no slot is taking too many, because if one slot is unbalanced, have too many, if you search or delete in that list, then you're going to have a bad time complexity. Okay, so this number as such, we give it a name. It's called the load factor. Okay, so this load factor is in some sense that the optimal time you would need to perform your dictionary operations. Okay, all right. Now, to analyze expected time complexity, we have to have an assumption. Okay, this assumption is intuitively we have to assume we have a good hash function. Okay, but let's make it a bit even simpler. Let's assume that our hash function is such that, okay, and such that the so-called simple uniform hashing assumption holds. What that means is that we assume that any given element is equally likely to be hashed into any of the m slots in your hash table. Okay, so you don't have preference for any of the slot in the hash table. Okay, so now if you assume we have this simple uniform hashing assumption, then naturally, intuitively, for any fixed slot, say j, okay, let nj be the length of the list got hashed there. The number is nj. Okay, now if we have this simple uniform hashing assumption, then what is expected the length of this? Well, since every element can go to each slot equally likely, no slot intuitively will receive any special treatment. Okay, so in the end, in expectation, every slot would receive the same number of elements, which is n over m. Okay, so under the simple uniform hashing assumption, then in expectation we basically achieve this kind of best the length of the number of elements hashed to each hash table entry essentially is basically proportional to the load factor to the best that you can have. Okay, so the elements are spread out evenly now into the hash table. Okay, and so that's just the intuition that your expected length of this is exactly the average length, because everyone has equal chance of receiving each element. Okay, okay. You can make this more formal and argue, prove that expected length of the expected number of elements hashed to the position j equal to n over m. So you can prove this more formally. I will skip this here. If you're interested, I'll be happy to explain during office hour or offline. Okay, all right. So now once we have this assumption, we already know, so under the simple uniform hashing assumption, we already know that now in the hash table, each entry, the number of elements mapped to each slot is basically n over m. Okay, that means now what expected search time? Well, the expected search time is that you have to spend constant time anyway. And then once you find to compute the hash value, okay, so compute, say hash value. Once you find the slot, you need to then search whether you have this element in all the elements mapped to that slot. And since the length is n over m, so time you need to spend is linear to that. So this is the expected running time. Okay. In the worst case, though, as we said, that in the worst case, okay, you still can be unlucky no matter what because hash function has to be deterministic. Okay, so no matter what hash function you choose, in worst case, you can still map. If your input is very weird, you could still have all the elements mapped to the same slot, which you need linear time to search for an element. Okay. And the insert, we already said that insertion, just put it into the list at the head, so that's only take constant time. Delete, essentially, you have to find hash value, search for it, and then once you find it, you only spend constant time to remove it from the list. So both of this now, the expected running time depends on the load factor. Okay, although the worst case for search and delete can be linear. Okay, now in practice, what we do is that in practice, we usually choose the size of the hash table to be on the same order of the number of elements you are interested in. Okay. In other words, in practice, we usually keep the load factor to be constant. Okay, which means that both in this case, the search time, the membership query, and the delete and insert, everything takes constant expected time for these operations. Okay, that's why you could assume, so in both in your homework and the exam, you can assume that the expected time for the three dictionary operations is only constant for a hash table. Okay, right? So in other words, under this simple uniform hashing assumption, and if we assume that the load factor is constant, namely the number of data you have is kind of proportional to the size of the hash table, okay, then you only need constant expected time for each of this operation, which is very efficient, which is far more efficient than using binary search tree, which needs log n time. But note that here, this is expected running time, while the log n time complexity for binary search tree is worst case, okay? But the point being that for the binary search tree, you cannot improve the expected time either, okay? So hash table in practice is very practical, very efficient, okay? All right. Okay, now in Python, okay, both the so-called dict, which is like dictionary, and the set are actually implemented using hash tables. Okay, so here are some examples, and in the homework we'll have more problems, and we'll also give you some example code of using hash table in Python. Okay, in Python, the search, this is the membership query. In other words, this is search for an element. So you can say that it's one in L, which is essentially saying that do search of in L, search for one. Okay, so now we know that all of this expected running time is only constant. Okay, so here just some examples. If you search for one in L, then the answer, oops, it should be true. Sorry. Okay, and search for 7 is also true. But if you search for 8, then the answer would be false because 8 is not inside. Okay, all right.